Preparing to live stream the meeting. Alright, that should be live there. Nice. Okay, cool. I'll stick in now like all here, man. Let me know, guys.
You're good.
I good? Okay, okay. So this video just got me a quick run through of the May-June 2026 physics paper 2. Real quick run through. I'll make a more in-depth video at a later point in time. Alright, let me go. Figure 1 shows a model of a hydroelectric power station. A hydroelectric power station, the main goal of it is to use water at a height, so it's going to have gravitational potential energy. It's going to fall, be converted to kinetic energy, and that's going to cause the turbine to move. And when the turbine moves, it's going to be converted to electrical energy. Right, so water from the reservoir flows down onto the turbine, which is connected to the generator to produce electrical energy. So we have a chart here. The chart in figure 2 shows the energy changes. So in the wet water reservoir, it's some distance from the ground, so it's gonna have what kind of energy?
Potential.
Not just potential energy. You have to say what?
Gravitational.
Gravitational.
Right, that's gonna have gravitational potential energy. GPE. The turbine is going to be moving.
Wind energy.
Wind energy. Nah.
Kinetic
So I don't-
energy.
Right. So over here, the water has gravitational potential energy. As it starts to fall, that gravitational potential energy gets converted to what?
Kinetic.
Kinetic.
Yeah, yeah. So like, what do you guys think? What do you guys think the answer for turbine is?
Kinetic energy.
Yeah, this is kinetic. Because here, what right? The water would fall, and it would start moving the turbine. So if the turbine is moving, what type of energy does it possess by virtue of its motion?
Kinetic.
Kinetic, right? And the bulb. Okay, when you supply electrical energy to a bulb, what will happen to the bulb? The bulb will what? Happen to the bulb?
They will move
So like
Illuminates.
and
It will
heat.
illuminate. So what kind of energy is that?
Chemical.
Nah, I wouldn't say chemical.
Heat.
It's simpler than you think.
light energy.
Heat
Light,
plus heat.
heat. Yeah, so the water in the reservoir is some height from the ground, so it's going to have gravitational potential energy, right? And when it starts falling, it's gonna get kinetic energy, and that kinetic energy is gonna cause the turbine to be moving. So the turbine is moving, so the turbine has kinetic energy. And the bulb is gonna receive the electrical energy, and it's gonna convert that to light plus heat energy. I don't know if I don't know if I'll ever feel a bulb before, but the bulb is be what?
Hot.
Hot.
It's be hot, right? It's be hot. It's be hot. Especially this is a filament bulb. Will get hot. Alright. Are you okay with this first question?
Yeah.
Yes.
Alright, cool. Easy stuff. One 6-watt bulb is connected as shown in figure 1. Determine the amount of electrical energy supplied to the bulb in 1 second. Okay, let's tell me fast. They're giving us power here. They're giving us time. What formula that you know involves power, energy, and time?
And energy is power by time.
Power, energy, and time. What formula you know have power, energy, and time in it?
Power is energy over time.
Power is equal to energy over time. If I want to make energy the subject of the formula, that's what they want me to determine, right? I gotta multiply both sides by what?
T.
Time.
So energy is really just power by
Time.
Time.
right. What was the power?
6.
6-1.
What was the time?
1
1
second.
second.
So the answer is
6.
6 joules.
6 what? 6 what?
Joules.
Joules, right. So you measure energy in joules. If you don't put that, well, it's a 1 mark question. Imagine they give you 0 marks because you didn't put joules. That'll be funny. Calculate the efficiency of the system if the total input power is 10 watts. Okay, no problem. So, do you guys remember the formula for efficiency?
Yes, sir.
Output over total input. 500.
So, it's the useful output over the total input by 100. And this makes sense because, okay, if I only use 6 watts out of the 10, then I could find this as a percentage by multiplying it by 100. What percentage is that, chat?
60.
60%.
Very easy, right?
Yeah.
3
Yes,
marks?
sir.
That's what?
So we tell her the paper was easy.
All right.
But so
Um,
from what I heard plenty people, the graph, when you see it come up, the questions in the graph, plenty people kind of mess up that.
but we will see, we will see. So there is a relationship between the brightness of the bulb and the height of the water reservoir. To investigate the most appropriate height for the model, the following results were observed. Plot a graph of potential energy of the water against height on the grid in figure 3 on page 7. So they want us to plot potential energy against height. So we're going to go on the y-axis,
Potential.
and it's going to go on the x-axis. Great. Let's move on to the scale quickly. So potential again, that was going on the y, and this is going on the x. Remember your rules for graphs, it must occupy more than half the page. So let's deal with height first. We have to go from 0 to 3.5. So I should, wait, what scale do you think I should use? I had to go from 0 to 3.5.
So for the x-axis, I did every 2 cm was 0.5.
That's fine, that's fine. When I had a look at the question, I had done essentially the same thing, but I had said every 4 was 1, which works out to what you just said. What am I doing, buddy? 1, 2. And like you said, if we're using that scale like it suggests, well, it's the same thing. You know what I mean? Uh, I'm very sleepy deprived right now. All right, cool. Are you okay with everything on the x-axis?
Yes, sir.
Yeah.
So let me run it back again. We need to go from 0 to 3.5. It must occupy more than half the space. So what did I do? Well, I said every 4 was 1, and I could split that up into every 2 is what?
0.5.
Every 2 is 0.5. If you notice 3.5 is here, so do I occupy more than half the space?
Yes, we do.
Right. I will look at the y-axis now. We had to go from 0 to 17.5. That looking real easy. If you recall, how much blocks it have? How much big block did it have? From here to here. I think it was 18. Was it 18 or
Yeah,
something?
I think it was 18 or 16.
Nah, it had to be 18. Right? So like, what do you call it fast? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's cool. So this scale real simple. I'm just gonna say every 1 centimeter represents 1 joule. I'm gonna follow, okay with that?
Yes, sir.
Yeah.
Yes, sir.
Are you doing any exam?
Yeah.
Mhm.
sir. I end up just doing every 2 cm.
Yeah,
Was
yeah.
like 2.
Too much sweats, too much sweats. You gotta do all of this on exam. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I only going up to 18, eh? Because that's all they really need. All they will do the full thing in the exam. So we have to label our axes. So on the y-axis, I'm going to put potential energy. Could just say EP. And I'm measuring that in what?
Joules.
So I
Joules.
put EP slash joules. On the x-axis, we're measuring height. We're measuring height. And that's in what?
Meters.
Meters.
All right, cool. Let me start. So my first point would be 0, 0. Because obviously, if you have a height of 0, your potential energy would be 0, as per the formula. MGH. And the other point, what the other point would be, guys? The other point. The other point looking like
0.5.
0.5 and 2.5.
and the other point would be 1.0.
1.0 and 5.0.
Right, so let me just start plotting. Let's start plotting, right? I can't start plotting. This is my first point. My other point is 0.5, 2.5. 0.5, 2.5. That's right here. I understand that? Like it's in the middle between 2 and 3. So 2.5. I understand that now.
Yes, sir.
I presume I'll get
Yes,
that.
sir.
Then we have 1.5. Hey, boy, this graph looking real nice. Then I see in 1.5, so 1.5. I hear somebody tell me it was just like a perfectly straight line.
Yeah, it was.
Yeah.
And then we had 210. I'll find this paper come similar to January 2026.
To a degree.
Easier?
2.5, 12.5. Find it was kind of similar. All right. And then we have 315. Bro, behave yourself. Good notes. Good notes. Behave yourself. 315. I had to big up Claude. Claude recreated this paper more real fast. 3.5, 17.5.
The only thing was with this paper, you got less marks for the graph because it was just the points and to plot, and well, you didn't have to do no calculation for the numbers, and they had given you the title.
They did?
Yeah, they had put it to the underneath.
Okay, well, I didn't see the graph now, so I just drawing this thing. I just drawing this thing. As you can see, it's a perfectly straight line. Perfectly straight line. Are you okay with this, right?
Yes, sir.
And the
Yes,
Yeah.
title
sir.
would be potential energy, EP, joules versus heights. Heights. Cool. The scale on the x-axis. What scale do we use on the x-axis? Every 2 centimeters or so.
0.5
0.5 what? Yeah, let's see. Let's see.
meter.
And on the y-axis, we say every 1 centimeter represented what?
1 joule.
1 joule. Yeah, 1 joule. That's it.
Yeah.
Now, obviously, if you said like every 4 centimeters is 1, that's fine. If you said every 5 centimeters is 5, that's fine. You know, there are other equivalent scales that would look exactly like this. So I feel like we get it. We had to get these marks. So far, all they have full marks, right?
Yeah.
All right.
Yeah.
Then they were way to calculate the slope. I write the formula first. What's the formula for slope? What's the
Y2
formula for slope?
minus 2.
Gradient y2 minus y1. x2 minus x1.
All right, so we need to take 2 points. Now, in physics, okay, even though you're seeing, like, okay, even though this is, well, I suppose it could use the points, right? Because it never mentioned anything about best fit. But just to be on the safe side, I'm going to read off points from the graph, just to be on the safe side.
Mhm.
How many nice points I can read off? I don't see any particularly nice points. What did you guys do? Did you all read off points, or did you just use the points I was given?
I use the biggest point and draw the triangle with the smallest point.
Okay. Well, in this particular question, you could use the points I were given, right? Like, okay, anytime they tell you, okay, did they mention best fit anywhere here?
No.
No, sir.
No, if you draw in a best fit graph, then it implies that some of the data was inaccurate and you'll have to do a best fit and the line wouldn't pass through the points. But the line is clearly passing through all the points here. So you
Mhm.
could use it. And that's the
Yeah.
most efficient thing to do. So I could use 0, 0. And which other points I could use? Pick any other point. But here what I'm saying, you cannot pick points from a like pick. Okay, if you do a best fit graph, you cannot pick points that were given. The only reason I'm picking these points is because they didn't mention anything about best fit, and you're clearly seeing the line passing through all the points, so it's fine. So 0, 0, and what other points do I want to pick?
210 normal.
You want to pick 210? Okay, no problem. So we could call this x1, y1, and we could call this x2, y2. So I have 0, 0, 210. I'll put the points I'm using here. I just want to see this. So what to do next?
Substitute.
I just substitute. So that'll be 10 minus 0 all over. What we getting?
5.
5.
5. And you have to put your units, right? So on the y-axis, what are we measuring? What were we measuring on the
Joules.
y-axis?
Joule.
So it'll be joules over what?
Meter.
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 Right. So you could write joules slash meter, or you could say 5 joules m to what power?
-1.
All right. How are you feeling, guys?
Yes,
So
sir.
far.
Good afternoon, by the way.
Good afternoon. Good afternoon. Everybody get a 5?
Yes, sir.
Yes, sir.
Okay, that is extravagant news. Let's see what they're asking us next. State the conclusion that can be drawn from the graph with respect to the brightness of the lamp and the potential energy of the water in the reservoir. Explain your answer. Okay, so I have the answer here already. Let me ask a question. Just by looking at this, as the height increases, what happens to the energy?
It
Sir.
increases as well.
Can you guys see that this is a positive gradient? And can you guys see that as the height increases, the energy output increases?
Yes, sir.
Yes,
Right.
sir.
If the energy output increases, well, let me check the circuit diagram. I don't really see enough fuse here. So at some point, maybe the bulb might blow, right? The bulb might blow,
Yes, sir.
maybe.
Oh,
But
I got that correct as well. What was the percentage I got?
60.
60.
Okay, I got it.
So like, generally speaking, as the height increases, the energy increases. And if the energy increases, that means more electrical energy is gonna go to the what?
Bulb.
And if more electrical energy is going to the bulb, as height increases, the brightness will
Increase.
increase. I understand that, right? Because you're getting more energy. If you're getting more energy, would the bulb shine brighter or dimmer?
Brighter.
Exactly, brighter. So the answer here already. As the potential energy height of the water increases, the brightness of the lamp increases. And you had to explain this, right? You had to explain this. So I just told you, at a greater height, you'd have more gravitational potential energy, which converts to more kinetic energy. And this will generate more electrical energy. And that more electrical energy is gonna go to where? It's gonna go to where?
The bulb.
Exactly.
The bulb
And if the bulb receives more energy, the bulb will what?
glow and light
Get brighter.
brighter.
Exactly. Easy stuff. Calculate the mass of the water in the reservoir given that the slope is equal to mg. Okay, no problem. So they tell me that the slope is equal to mg. So what was our slope? Well, our slope was 5, right? 5.
Science.
And they are telling us that is equal to mg. Write that down one time. So the slope that was found to be 5 joules per meter. And they're telling us that that is also equal to mass by gravity. Where m is the mass of the water and g is the acceleration due to gravity, take g to be 10 newtons per kilogram. No problem. So they want me to find mass of the water. They want us to find for m here. This is what we want to find. Did they give us g?
They give you the gravity.
What? Yeah.
Yeah, they gave us g. So what's the only unknown in this equation? M. So you have 5 is equal to m by 10. So to make m the subject of the formula, you divide both sides by
10.
10.
And so m by m, what?
10.
10. Guys, take a little time. You have to divide both sides by 10, not m.
Yes, sir.
I've already received the price, so I cannot depend on you guys at some point in time.
Yes, sir.
What's 5 over 10?
0.5
0.5, and that will give us the mass in what?
kg.
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 So I was
Right,
kind
so
of contemplating about that one, you know, because when I see 0.5, I was like, what?
yeah, 0.5 kg, which is
Same.
Nah, but I
500
got that. I
grams.
got that correct as well.
Right, somebody was talking to me. Amelia, that was you.
No, sir.
All right. So here, what if you realize we're working in SI units, and if you wanted to verify something, watch this quickly. So how did we get M? Well, we divided joule per meter. We divided that by gravity, which was N kg minus 1. Now, joule per meter, I don't know if I didn't know this, but this is actually N. How much of you guys knew that?
Yes, sir.
Yes, sir.
Yeah, yes,
So
sir.
like if you have Newton, if you divide them by Newton per kg, when you change it to multiplication, it's gonna reciprocate, and the N will cancel off, and I'll give you what?
kg.
kg.
That'll give you kg. Right? Kg. Bam. Yeah, so kg was a unit. I mean, you're working with SI units anyways, so you should see kg. Kg it is. Oh, look, this is where the kinematics question from maths went. This is where it went.
Yes,
This is
sir.
just a math. This is just something you do in maths. Oh, look, this is just something you do in maths. So over here we have a velocity time graph. Oh, let's tell me, for a velocity time graph, the gradient gives you what?
Acceleration.
Acceleration
Acceleration,
and
deceleration.
deceleration.
Acceleration and deceleration. Now, for these periods over here, that would imply that the velocity is what?
Constant.
Constant. I know for a fact some of you guys are going to say it's stationary. No, it's not stationary. It's still moving, but it's just moving at a constant velocity. Okay? This over here is acceleration, and this over here is what?
Deceleration.
Deceleration.
Right. So they want me to talk about displacement. All right. Say I had an object over here, right? I take it and I move it to this new position. X marks the spot. I just displaced it. Say I take the new position and I put it back here. Again, that's displacement. So displacement is just you moving something from an original position. Are you understand that?
Yes, sir.
Yeah.
Could displacement be positive or negative?
Yes.
Yeah, because displacement is a what quantity? A what quantity?
Vector.
A
Vector.
vector quantity. So displacement is just the distance moved in a specific direction from a reference point. It is a vector quantity measured in meters. Did you all put all of those points?
So actually speaking right now, I did that, sir. Like I stated what it was, and I said just put things just to make sure I got it right. I put it with a vector quantity.
Good. I like to hear that. I see Liam laughing.
So I get.
All right, nice. And acceleration, people who do kinematics and advanced. Acceleration is just the rate of change of velocity with respect to what?
Time.
Time.
So acceleration is the rate of change of velocity with respect to time. It is a vector quantity because it could have positive acceleration and it could have negative acceleration, which we call
Deceleration.
right. And it's measured in ms minus 2. Ms minus 2, you could say that, or you could say what?
M over square.
Meter per second squared.
Yeah, m/second squared. Bam. The letters A, B, C, and D on the graph in figure 4 represent various stages of the cyclist's motion during his journey. Describe the motion of the cyclist at each of the stages labeled A, B, and D. So at stage A, what is he doing?
Move at a constant velocity
Constant
5
velocity.
for 100 seconds.
Right. Moving at a constant velocity. Right. Of what? Yeah, they had to state what
5
constant
ms.
velocity. Are you seeing that, right? 5. So for A, between 0 and 100 seconds, he's traveling at a constant velocity of 5. So he's moving at a constant velocity of 5 meters per second. All right, stage B now. Let's look at stage B. Yeah, Nikolai.
Right? But I put the 5 meters per second, right? But I also put like the timing as well. Is
That's
that
fine. That's
oh,
fine. But you did say moving at a constant velocity, right?
Yes, sir. I said moving at a constant velocity, but I put in like I wasn't too sure if that was correct. So I know okay, like I know I was correct, but I had my doubts. So I made
That's
sure
okay.
the velocity anytime.
That's okay. The more information you put, can't go wrong.
Yes, sir.
Look at stage B now. Stage B is what?
Acceleration.
Is acceleration, right? Because as time passes by, your velocity what?
Increases.
Increases.
Your velocity increases. So at stage B, you have acceleration. And so you gotta be specific, eh? You wanna say, okay, this shape is a line. If it's a line, it implies that the gradient is
Positive.
Positive.
constant. Constant. So in stage B, you actually have uniform. That's exactly what they want. Uniform acceleration. Uniform acceleration from 5 meters per second to what? 5 meters per second to what?
15.
To 15.
To 50. And if you put the time frame as well, over 100 seconds to 300 seconds, over the 200 second time frame, that's fine. That's fine. So uniform acceleration from 5 meters per second to 15 meters per second. Did you guys get that?
Yes,
Yeah.
sir.
Yes, sir.
I
Right.
didn't. So I just didn't put the uniform acceleration.
I only put
Okay,
acceleration.
I put acceleration here.
I don't think CXC will deduct marks for that, but that the uniform is the proper thing to put.
Yeah. Okay.
Should write our message.
Yeah, I just put in acceleration. But the same thing like I did before, I put it in the question, in the answer.
That's fine. I don't think they would penalize you for that, but uniform is the word that is ideal there. Because the acceleration is a straight line. Stage D now. Stage D looks like what?
Deceleration.
Deceleration.
Because as time passes by, your velocity drops and it eventually reaches what?
0.
0.
0. And you're decelerating uniformly from 15 to what?
0.
0 meters per second.
Right, so uniform deceleration. Cool. Easy peasy, lemon squeezy. Calculate the total distance traveled by the cyclist during a 10-minute journey as shown in figure 4. Alright, when we're talking about total distance traveled for a velocity time graph, we are really talking about the what?
Area on the graph.
Here.
Yeah,
Sir,
on the graph.
yeah. I'm gonna tell you a little story about this, eh? You see
It
the
was,
question here?
yeah,
I soon realized it was area under the graph, but like
yeah,
it
yeah, yeah.
wasn't clicking. So I was confused as to what they said, and I left the question and I went and answered the other stuff. And when I came back to the question now, so you see you see the graph right here? I break
Yeah.
this into tiny
Yes,
blocks,
yes, yes, yes.
trapezium,
That's what you had to do. That's what you had to
the
do.
triangles,
That is what you had to do.
and then
So I get 5 parts.
I find the area, all of these things, and I add it up. I say, but wait now, I get the answer here. But before, I just guessed and I got the answer still, but I wasn't
Well,
sure if it was correct.
yeah, yeah,
I
yeah,
break
yeah.
it
Five
Right.
nine
into
something, right?
smaller blocks. So you see, like we're cut from C at 300. I
Yeah.
continue with the line from A straight across. So it was like a triangle and a rectangle.
Wait, boy.
And I put trapezium. It had a rectangle, a triangle.
Wait, boy. So let me do this question fastly, boy. But yeah, yeah, you could break it up into how much parts you want. You can break it up to how much parts you want. So we have 100 here, and we have height of 5. So the area for this could be what?
500.
500.
500. And area is the product at 2 dimensions. You have meter per second on the y-axis, and on the x-axis, yeah, time in seconds. If you find your product, it'll leave you with what?
Meters.
Meters.
Meters. So that is why area on that graph, or velocity time graph, gives you distance traveled. What shape is this, guys?
Trapezium. Yeah,
Or
Is
that's
that is that trapezium, right? So to find the area for trapezium, we need
So
to know the two
wait,
parallel sides.
is, 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 is,
Yeah, talk
the
to me.
graph kind of wrong? What did you write?
Yeah. Oh, that's Claude fault.
Mm-hmm.
Oh,
Yeah, I send
yeah.
the picture.
Yeah, it
supposed to
is.
be.
Let me look at the picture.
Wait, so you asked Claude to do this? I thought you got a soft copy of it.
No, ask Claude to do this. Yeah, Claude did do something that's a bit sus. Yeah, give me a second. Yeah, Claude was a bit sus. Yeah, give me a second. All right, thanks. Thanks, Leon.
Yes, sir.
It's the same concept regardless, but iPad. Claude, boy. Claude. Hey, Claude do a good job, relatively speaking. Claude do a good job.
Yeah, it did, but it just made that mistake.
Yeah. And I use ChatGPT to generate back the diagrams. Quick. Let me correct this thing first. Sorry, they Claude.
Yeah, that is what the killer look like.
But it's the same procedure I'm gonna follow. Right? Same procedure. Alright, there we go. So nothing had changed. A is still uniform. Okay, what's in? Yeah, A is still a constant velocity. B is still acceleration. C is still constant velocity. And D is still deceleration, right? Nothing had changed. Hopefully, you understand that. You understand that, right?
Yeah.
Okay.
So
So, what would this dimension here be?
that would be
150.
150.
Yeah,
Yeah,
looking like 150. And this is 5. So the area will be what? Should be 750.
150.
750.
7. Right? What shape is this?
Trapezium.
That trapezium, right? So that distance there is going to be 5. What is this distance going to be?
15.
And this distance is 200. I look like
200.
200. If you're confused, right? This is 150 and this is 350. What's the difference between 150 and 350?
200.
200.
Yeah, so I'll understand that, right?
That's it.
So I'll use the formula. I have A plus B by height. You should know that A and B are the parallel sides. So what are the parallel lengths there?
15 and 5.
5 and 15.
15,
And my height is what?
200.
200.
So that'll be 20 divided by 2 is 10, 2000. Are you understand now?
Yeah.
yeah.
Now, what kind of shape is this? You have two parallel lengths.
It's also a trapezium.
Yeah, it's also a trapezium. We know that this is 15. We need to find this dimension over here. What's the difference from 350 to 600?
250.
250, right? And what would be the difference from 350 to... Okay, this one you have to be a little careful about.
I know it's 530.
Yeah, that's 5 to...
That's
Because
530.
it was one tiny block was 10.
Yeah, that's correct. Because here what, right? If 10 small blocks is 100, then every small block would be 10, like Nikolai said. So this one over here, you look at it, it's really 530. So to find this dimension over here, it's going to be the difference between 350 and what?
530.
530,
What's the difference? Come on fast, guys.
180.
What's the difference?
180, 180,
180. So now we could use the same a half A plus B by height. My two parallel sides are the 180 and the what?
250.
It's a bit hard to see, right? But the difference between 350 and 600 was the 250 we found over here. So 180 plus 250. And I'm going to be multiplying that by the height. What's the height?
15,
50. So, again, And you multiply all of that. Let's calculate as always, I think.
Start doing this, hold on.
3,225.
What's that? Let me verify it.
Yeah, 3,225.
0.5 180 plus 250. Y'all again 3225?
Yeah.
So what would the total distance traveled be then?
5,975.
Well, let me see, right? We gotta add up everything. So 3225 plus 2000 plus 750 plus again 5975.
Yeah,
That's what you guys got in the exam?
yeah.
Yeah.
I find I should get more marks for that way. I would 4 marks, so that's it wasn't hard though. I just saying, yes, you see what they give 3 marks for. You just see what it does give 3 marks for, right? So total they give more marks. Nikolai, let me know if you understand that.
Yes, sir.
All right, cool. Yeah, you get this right, Nikolai?
Yes, sir.
Okay, good. Calculate the average speed. What's the formula for average speed, guys?
What I know is
Distance over
Total
time.
distance about
What's the total distance? Total distance was 5975.
Yeah.
And the total time taken, but that was again, boy. That is
600
600
seconds.
seconds. So the total distance, I was saying the total time taken will be from here to here, 600. So that'll be 5975 divided by 600. What did you guys get for this?
Yeah, so
What you get?
9.96 meters per
9.96.
second.
Right, and the units would be meters per second, or ms minus 1. Why? Because distance is measured in meters and time is measured in seconds, so m/s, or ms minus 1. You guys got this? I'm gonna know, guys.
sir.
yeah.
So,
Yeah.
Nah?
Yeah.
Okay. Alright. Determine the deceleration of the cyclist. So the deceleration. What would the deceleration look like? Where did he decelerate?
By D.
D. So we gotta find ingredient of this. This would be 600, come on, what?
0.
And this would be what?
1595 to T.
Be 530 first, then 50.
15.
So I could call this x1, y1, call this x2, y2. I find a gradient here one time, and that would give us, well, when you find a gradient, that's going to give you acceleration, right? So that would be y2 minus y1, so that'll be 0 minus 15, all over x2 minus x1. X2 is 600, x1 is 530. What are we getting for that?
Minus 1/5.
Verify that. Somebody verify that.
I got minus 0.21.
Yeah, that's what again.
Yeah, that why I get.
Oh,
Yeah, watch. It's it. Yeah.
And this one here, this
And
one,
wait, that's not the answer. No, that's not the answer. That's not the answer. I'll explain something. This is acceleration. This is acceleration, right? As acceleration, we just find for there. They want a deceleration. So deceleration would just be the positive of this.
serious.
Yeah. Because, okay, when I say deceleration, it's understood that as time passes by, the velocity is decreasing. So you got to put in negative. I tell the advanced people about this before. If it's deceleration, you just say the positive value. Yeah, deceleration. Liam, I guess you didn't get that one.
no, not this one.
Okay. Is it that I took a wrong point or something?
Yeah, sure. I swear it's negative. Everybody in school got a.
I am 100% sure. Like, okay, look up deceleration. Look it up on Google.
Mm-hmm.
Like, okay, acceleration is minus 0.21. The deceleration for that is just 0.21. Because when you see deceleration, it's understood to be decreasing with time. Look it up. Right?
Mm-hmm.
I don't think CXC would penalize you for minus 0.21 though, but I would advise you to put 0.21 as the correct thing in any context. Figure 5 shows that
Wait,
230 volts.
one question, right? So
Yeah,
it can be minus 0.21.
I'm not sure. The proper thing to do is to put 0.21. But I don't think CXC will penalize even for minus 0.21 because I think that's what most people do. But the proper thing is to put 0.21 because it's talking about deceleration. Deceleration is understood to be negative. Why would I say negative deceleration? Negative deceleration will be acceleration, and that's wrong. Yeah. Because, guys, the negative indicates like direction. If it's negative 0.21 ms minus 2, that means every second that passes by, my velocity decreases by 0.21 meters per second. So the deceleration is just 0.21 ms minus 2. It's just 0.21. So that's what I would put. Figure 5. So we have a appliance, a circuit here with appliances. The appliances are connected in what? They are connected in what?
Parallel.
Parallel.
They are connected in parallel. Parallel. So if let me ask you that question, right? Quickly. If the air cooler stop working, will the current still flow in the circuit?
Oh yeah.
Yeah, because it's a parallel circuit. If the microwave stop working, will the whole circuit break?
No.
That's a
No, it won't. Because watch. If this break, current would just flow as per usual. It would still have a return path. Well, it's it's an alternating signal, so like the current will move back and forth, back and forth. But like, I'll understand that, right? Like if one appliance goes bad, the whole circuit is not going to be affected that much.
Yeah.
Okay.
Yeah.
So define the term power as an electrical quantity and state the standard unit. So power is just the rate at which work is done. And I think you'd realize that from the formula. What's the formula for power?
energy over time.
Energy over time. So what? An energy, what's the definition for energy? Energy is what? Okay,
The
energy
rate
is
of.
work done. Work
Mm-hmm.
done. Energy is work done. If I'm dividing work done by time, then I'm dealing with rate. So it's just the rate at which work is done. Anytime you divide by time, it's a rate. So power is just the rate at which work is done. And the SI unit is watt. And the formula is P is equal to E over T.
So
Right. Calculate the total power which is supplied to the circuits. Okay, if it's using 1.2 kilowatts, this using 1,000 watts, this using 80 watts, this using 80 watts, what am I gonna do?
add it.
Just add it. That's all. What did you guys get when you added everything? So that'll be 1200 because 1.2K. Where's 1.2K? 1.2K is 1.2 by 10 to the power 3, which is 1200. Adding that to 1000, adding that to 80, adding that to 80. Based on the silent faces, I guess no, I didn't do this.
I do that.
That's the other than.
I did that.
Okay, it's real straightforward. You don't know what thinking. What you guys get?
Mm.
2,360.
2,360.
360.
360.
And the units will be what?
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 That's
So I'll understand if I want to find the total power consumption, I just add the power consumptions for each individual appliance. That's all.
Yeah.
That's it.
Mm-hmm.
Fill in the blank spaces in the statements below which relate to the manner in which the appliances are connected. The appliances are connected in what? You see in that current is dividing, like it's being split. Anytime
Parallel.
current is being
Parallel.
split,
Parallel.
anytime current is being split, it's a parallel circuit you're dealing with. So they are connected in parallel. As a result, the voltage across each appliance is the what? In parallel circuits, the voltage across components is the same.
So I
Remember,
thought the answer series. It just now I said what?
now watch. You see the voltage across each component is the same. Voltage is just like the potential difference between 2 points. So like, same voltage across that, same voltage across that, same voltage across these things. You understand?
Yes, sir.
So anytime you have a parallel circuit, the voltage across each component is the same. So just one advantage of connecting the appliances as shown in figure 5. One, if one appliance goes bad, the circuit will not fail. Circuit will continue working. And another thing, if the fridge needs 230 volts, the microwave needs 230 volts, this needs 230 volts, and it makes sense to connect it in parallel so all of them will get the same voltage.
Yes, sir.
Yeah.
Yeah, so each appliance receives the full supply voltage, so each operates at its rated power. Also, if one appliance fails, the other continues to work. We could get that one.
I only see the last part.
That's the
That's not a problem.
Alright.
Calculate the current in the microwave. Okay. So we want to calculate current. What information did they give us? Well, we have the power here and we have the voltage. So could I calculate current?
Yes, sir. Physics are IB.
yeah.
What is the power being supplied to the microwave?
1000.
Do we know what the current? I think they asked us for current, did they not?
Yes, sir.
Yeah, calculate the current
No.
in the microwave. In the microwave? Yeah, in the microwave.
Sir.
So the microwave consumes 1000 watts of power. Now, since the same voltage is across each component, then the voltage across the microwave is going to be what?
230.
Going to be 230.
230 volts.
Right. So then I'm going to divide both sides by
230.
yeah. What are we going to get?
4.35 amps.
Did you
So,
guys get 4.35 amps?
I didn't know what to do, but I do that and I get correct.
Yes, sir.
Nice. Yeah, me get through there, but get through.
Yeah.
A fuse must be used with a microwave. Briefly explain the purpose of the fuse in electrical circuits. So for those of you guys that don't know what fuses look like this, if it have too much current being passed through, if you exceed the rated current for a fuse, the thin wire inside melts and it breaks the circuit. So you use a fuse to protect circuits from overcurrent or like a short or something.
A surge.
Yeah, you can say a surge as well. So a fuse protects the appliance and wiring from damage due to excessive current. If the current exceeds the fuse rating due to a fault, the fuse wire melts and breaks the circuit, preventing overheating of fire. That's what it is. Right.
I get them 2 max in the bargain.
Big up yourself.
So,
Calculate the energy in joules used by the air cooler in 30 minutes. All right. So here what, right? They're talking about energy.
What was energy over time?
They given me time. So I have E, I have time, and the last question, they gave us the what for the air cooler.
1.2 W.
So it
KW.
gave us power. It gave us power. Gave us power. It was 1200. 1200 watts. So what formula they know would have EP and T in it.
Power is equal to energy over time. We substitute for energy. Well, you make energy the subject.
Right? So to do that, I can multiply both sides by T. So the T would cancel off here. And whatever I do on one side, I do on the other side. So PT is going to be equal to E. So I could just write E is equal to PT. What's the
Yes.
power?
Pause 1,200.
What's the time?
30 minutes.
Yeah, I come with that to what?
Seconds.
By 60.
Yes, I multiply with that by 60.
Real again.
1,800. Our next set of marks in the bag, sir.
This physics is almost cake, buddy. What's 1200 by 1800? Check my calculator.
2.16 by 10 to the 6 power joules.
Yes, so that why I put. At first, I put in the full value, and then I came later down and put down that.
Yeah, it is typically one the answer in standard form. Right? But this calculator always dying on nobody. It's so useless. This is one time I'll call a Casio calculator useless. Like I don't know why that has happened. I don't like to believe I had to pay $20, 20 US a year to maintain this subscription. I like to believe that. It's crazy. So 216. And we have 4 zeros. Here it is working, right? 1, 2, 3, 4, 5, 6. I shifted how much spaces to the left?
Times.
How much?
Right.
6 times.
So that'll be 10 to what power?
Power 6.
Alright, joules. Everybody okay with this question?
Yes, sir.
That's the
Yeah.
If you had right the answer, us is fine though. It's fine. If they don't care about all that, it's fine. Part 2, current in one of the filament lamps. Okay. The way to find the current in one of the filament lamps. Notice that both of these filament lamps pull in the same, well, they're using the same power, so they'll pull the same current. I presume that they have the same voltage rating. So what formula we're going to use there? Again, we have power. We have power. We're going to find the current in one of the filament lamps. So we have the power. We have the voltage across it. Where's the voltage across it? Where's the voltage across both of these? Guys,
230 volts.
watch. If you're confused, where's the voltage across both of them? Both of them being supplied with what? Across both of them.
230.
230. So here what? We have the power. We have the voltage. We try to find for I. So we divide both sides by what? By V. And again, now but I is equal to what?
P over V.
P over V. Your power is 80 and the voltage is 230. So what are we getting for the current? Should get like 0.3.
0.35.
I'm gonna check something. Yeah, 0.35. Do you get that?
Yes.
Yes, sir.
So Liam, you lose like 1 mark so far, like 1 or 2 marks so far.
Like 2, yeah.
Alright.
I
Figure
lose one
6
for
was
the gradient and then for the unit for the gradient and
oh
yeah, that's it.
ChatGPT make back this diagram. How do you think ChatGPT do?
Not bad, except the constriction.
Yeah,
Mhm.
yeah. Like okay, this is what Claude did.
Whoa.
This is what ChatGPT did. So this work good together.
So one question. If
Yeah,
I say the first one was a laboratory thermometer,
that's fine. That's
I
fine.
not seeing.
Next one is a clinical.
Yeah,
Yes, sir. I
right?
found the other two, but just the first one, I say, well, the degrees was a bit higher now, so I
Yeah,
put
yeah,
the
yeah. No, no,
laboratory.
that was good intuition. That was good
So,
intuition. It is a laboratory thermometer.
so
Or you could just say a mercury in glass thermometer. Yeah, Liam?
Renisha wants to know if she could talk to you after the live stream got.
Sure. So this one is clearly, well, if we're being vague, So mercury in the glass thermometer. You could also say it's a laboratory. But why are we saying that though? Guys, and this looking and if you didn't know any better, and you might as say it's a clinical thermometer.
I
Well,
put
You
on
didn't
this
know
and
any
this one.
better, right? But like who okay, like I sound like an owl just now, right? But like let me be real, right? Who measuring minus 10 degrees Celsius?
sir, that person long gone, sir. That person long gone.
Yeah. Who measuring 110 degrees Celsius? So like would this be a clinical thermometer?
Nah.
Sir,
Nah, that can't be a clinical thermometer.
excuse sir.
Yeah, Nikolai.
That's your risk for your girlfriend, sir.
110 degrees Celsius. Nah, what
Yes,
the
sir.
fuck? So this one over here, you see any constriction, immediately you should be thinking, clinical thermometer. And then look at the range, it's 35 to 42. That's like human temperature range. Right? And this last one, if it was any thermal life, I mean, yeah, you'd understand this one. You have two different types of wires, then you have a cold junction.
A thermocouple.
It's
Oh,
thermal.
couple.
Sir, I made champ spell that correct, you know.
Big
Do
up you.
do you lost max if it's spell it incorrect, but you have like the understanding of what is this?
No.
Nah, there's no English.
Oh, because I spelled it wrong.
There's no English. Thank God.
So you could get it right, only spelled wrong.
Yeah.
Okay. Well, that's
That'll
good.
give you excuses to start spelling your name and thing wrong, eh?
Nah.
All right. B was a clinical, and C was a thermocouple.
Yes, sir.
Easy peasy. Easy 3 marks. I already have the answers here, because I'm not gonna write all this. State two features of thermometer A, which determine the time taken for the thermometer to respond to changes in temperature. Number one, the size or the mass of the bulb. A larger bulb will take longer to absorb heat and reach thermal equilibrium. Okay, think about it. If the bulb larger, it would have to heat up more contents.
Sir.
Yeah, so that would take longer to heat up and reach thermal equilibrium. Thermal equilibrium just means that throughout the bulb, it's the same temperature.
Yeah.
And it would be the same temperature as whatever you're using to like heat it to. If you understand what I mean? Like if I take a thermometer and I stick it on my arm, right? Thermal equilibrium would happen when inside the thermometer, like everything inside the thermometer is the same temperature as what's outside. You know, like the inside conditions is equal to the outside conditions. Equilibrium just means equal, balanced. And the thickness of the glass wall of the bulb. The thicker glass would conduct heat more slowly, increasing response time. I'll understand those two. Did you guys put that?
Yeah.
Okay. Anybody else put those two?
No.
I'll show you can a lap. You could
I just got kicked off for a moment. What was going on?
I never kick you out. I never kick you out. But
Like I got bumped off and got back in.
but yeah, Nikolai, let me know if you understand these two features of thermometer A.
Yes,
When you
sir.
look at thermometer A, you notice that the bulb is a bit bigger. And
I just put how the degrees was, the range of the degrees. Like you can measure.
nah, nah, that's not.
Hmm.
Nah, Nikolai. That wouldn't be it. They were to state two features which determine the time taken for the thermometer to respond to change in temperature. The increments wouldn't have a effect on that. It would really be the size of the bulb and the thickness of the glass wall.
Oh, okay.
Determine the physical property employed by thermometer B that varies with temperature. Guys, if I apply heat here to the mercury, what happens to the mercury? Applying heat, out in the kinetic energy will happen.
It'll move up.
It will move up. Why? Because what's increasing?
The mercury increase. Well, temperature increasing.
Okay, I can talk about V.
Velocity.
Nah, not velocity.
Volume.
Nikolai, volume.
Oh,
That's it.
volume.
You have to say volume. So thermometer B uses the expansion of mercury with temperature. Specifically, the volume of the mercury column increases as temperature rises. Yeah. It was looking for volume. Because as you apply heat energy, the mercury molecules are going to gain kinetic energy. And they're going to start to vibrate, move about, occupy
Yeah.
more space, increase volume. Using the kinetic theory, explain why the rate of evaporation of water increases with temperature. As temperature increases, the average kinetic energy of the water molecule increases. More molecules near the surface therefore have sufficient energy to overcome the intermolecular attractive forces and escape into the vapor phase. So the rate of evaporation increases. I think we did a question just like this coming down to the end of the live. Put something like this along the lines.
Yes, sir.
Okay.
So I put
So you put the like the laws like
Yes,
Boyle
sir.
law, Charles law, Prussia law.
Nah.
So I put how the particles in the liquid due to the temperature increase gain kinetic energy and break from their bonds, making it faster to change from a liquid to a gas.
That's
That's
fine.
it.
That's fine.
Okay.
That's fine.
Yeah,
Yes,
so
I have
but
also.
I put the kinetic energy and what the particles would have done, but I put underneath the laws.
They won't
Nah,
take
the
out marks.
laws. Nah,
They won't.
they wanted kinetic theory. They wanted kinetic theory.
Oh, okay. I still
It's
get the mark.
basically evaporation.
I put the kinetic energy. I think they'll just would they scratch it off or would it be dark marks?
They might just scratch it off. They might
Okay.
explore it. So here what? If you wanted, you could have say E is equal to MLV. Because you're dealing with evaporation. Oh no. Earlier, it have a difference between evaporation and vaporization. Eh? We looked at that in the morning. Evaporation is only occur at the surface. Vaporization, boiling, happens throughout. Yeah. But like vaporization is just the liquid turn into what?
Gas.
Yeah, just the liquid turn into gas.
So the one I put wrong.
No, it's fine. It's fine.
Alright.
Once you say, okay, you're dealing with, you know what? No. You're dealing with latent heat vaporization here. Like evaporation means that it going from, there's a state change. It going from a liquid to a gas. So yeah, if you wanted, you could have say E is equal to MLV. And you could have talk about latent heat vaporization.
Yeah.
That's fine. Because we're just talking about the state change, so that's fine. Part 2. Pressure exerted by a given mass of gas increases when its temperature is raised and its volume is kept constant. Okay,
This is the pressure law here.
yeah, because okay, if the
Yeah, I
volume
put
is
in
kept
the
constant,
pressure law.
if the volume is kept constant, what two things are changing?
The temperature and the pressure.
Yeah, so that's Gay-Lussac's law, the pressure law. So as
Yes, sir.
temperature rises, the molecules of the gas gain more kinetic energy and move faster. They collide with the walls of the container more frequently and with greater force. Since pressure is force per unit area and the volume is constant, so the area doesn't change, the pressure increases. Let me explain, right? Imagine you had like a fixed container here. When I apply heat, what happens to the molecules on the inside?
It'll start to vibrate. Wait,
They
really?
go start to vibrate,
Yeah.
and they go start to collide. And when
Yes,
they
sir.
start to collide, they're gonna hit the surface. But is the area changing? The area is constant, right?
Yes, sir.
If the area is constant, what's gonna happen to the pressure inside?
It will increase.
It would increase, because they have these molecules pressing against the walls. So the pressure will build up inside. So let me fully understand that. Did you all put this?
Yes, sir.
Did you guys put that?
Yeah,
Yes, sir.
that same thing.
Yeah,
Okay,
that like explanation you put in there is the same thing I put in.
nice. A metal cylinder containing gas
Food.
is taken out of a refrigerated store, maintained at minus 23 degrees Celsius. So maybe that's T1. The pressure in the cylinder was 75 pascals before it was removed. Maybe that might be P1. Calculate the pressure in the cylinder with the surrounding temperature rises to 27 degrees Celsius. Assuming that the cylinder itself does not expand. Right, so we clearly the only pressure law here. What is P1?
Constant.
75 pascals.
75 pascals
What's T1?
minus 23.
minus 23 degrees
I'll
Celsius.
put plus 273 to change it to
Wait.
Kelvin.
But you have to add 273. We talk about this real plenty.
Yes, sir. Hey, sir, as soon as you say pressure law, I don't know I get these facts early.
Big up. So we're getting there. It should be like 250.
I get 250, and the next one is 303, no, 300. 32nd one.
So like Nicola again, I won.
But
Everybody
of
here.
course, sir, hey, I was in my vibes, and sir.
Yeah, that's it. And we again.
I get wait, let me just make sure. I know I get 300, but
Yeah, it's 300.
300, yeah.
Cool. And we had to find for P2, right? P2 is what we're finding for. So what does this rule look like?
It's like a fraction, so it's P1, T1 is equal to P2 over T2.
I didn't make this up, right?
Nah, I never mix that up.
I'll get you this, right? P1 over T1 is equal to P2 over T2.
Yes, sir.
Yes, sir.
Cool. So P1 was 75. T1 was 250. P2 was what? Unknown.
Unknown.
What was T2?
300.
Right now I have P2 divided by 300. What I would do to get rid of the 300?
Multiply.
So P2 is just 75 over 250 multiplied by 300. What are we getting for that?
90 pascals.
Yes, sir.
Well, I get 90
I
pascals.
just cross multiply to just make sure
Yes.
that
Yeah.
correct procedure. Yeah. And I just went on with it.
That's not a problem. And if you wanted to check if your answer is correct, when you multiply these two, it's supposed to be same product as 75 by 300.
Yeah.
Try it. Where's 90 by 250?
Two-
22,500.
Okay. Where's 75 by 300?
Same thing.
Same thing.
22,500.
Yeah.
Mm,
I'll get that for Max.
Yes, sir.
Yeah.
So I'm glad now, sir. You see this? You see this? Raging
easy,
Max
it's exam.
and
So-
Venus
so-
use the X-ray guns.
So let's write it down fast. Rich men in Vegas use expensive
Guns.
guns. Hey, Nikolai. Where would you want guns by Nikolai, boy?
I don't know. But sir, my friend used this and I use the Raging Martians.
Okay. Where would Nikolai and a lead on gun hunting, boy?
So it was someone who was talking about a paper man. The paper man was given
Yes,
them.
I think she's here now. Is she here? No, I think she leave. Yeah.
Yeah,
But
but
let me answer this fast. Which one? Remind me, guys. Which one has the shortest wavelength?
radio waves. No, wait. Wrong thing.
Gamma rays.
Gamma. I pull out 180 and all that.
Ah,
Infrared, visible, ultraviolet, X-rays, gamma. Okay, which one has the longest wavelength?
radio waves.
Radio waves.
And are we talking about the inverse relationship? So if we have the biggest wavelength, they gotta have the lowest what?
Frequency.
Alright, so we know how to handle this then. So here what, right? You had to understand that it was going the other way around.
mhm.
So like, stay with me, right? What is before microwaves?
Radio waves.
Radio waves.
Okay, if you have a hard time understanding it, and you see at the bottom, you're seeing a large wavelength. Seeing that?
Yeah.
And over here to this side, you see now what wavelength?
A very dense, it's very
Small wavelength. Remember, wavelength is just okay. Wavelength is just this, is it like distance between two successive crests or troughs? So the wavelength there is that, but the wavelength here is this, much bigger. So A, what was S? S is what? What is
radio.
S?
So when I saw that thing underneath, I had no clue as to what it was.
That's wavelength. I wavelength. So S is radio waves. What is R?
That would have been the infrared.
They put an R to confuse all because I know someone they would have put radio waves there. You know
So I
that.
think someone in my class did that.
And this is visible light here. What can you go be?
Visible light and
Ultraviolet.
ultraviolet.
Anybody has this in the lambda ray?
Me.
Yeah.
I don't know ultraviolet.
Oh,
Yeah.
Yeah. I've read this in the lambda ray, but and then after X-rays, yeah, what?
Gamma.
Gamma. Hey, easy marks, but I think that's right.
Of course.
Yeah.
Right. X-rays and ultrasound can both be used for scanning internal organs. Explain why ultrasound can be used as cannot. Or explain why ultrasound can be used to scan unborn babies, whereas X-rays cannot. I'm answering that question. Which one is more ionizing? X-rays or ultrasound?
X-rays.
X-rays.
X-rays, right? Ultrasound is just use sound, It's like a very high frequency.
So I put out the long exposure to X-rays can cause damage to the baby.
Yeah, kill the baby. Baby got cancer.
Ooh. Ooh. All right,
The
all right.
X-rays will damage the
That correct?
baby. The
The same
ultrasound
one.
wouldn't do that. Ultrasound wouldn't do that because ultrasound, is just a high frequency sound.
Yeah.
So X-rays are ionizing radiation. They carry enough energy to damage or kill living cells and can cause mutations in DNA, posing a significant risk to the rapidly dividing cells of a developing fetus. Ultrasound uses high frequency sound waves, which are non-ionizing and do not damage tissue. It is therefore safe to use on unborn babies. Ultrasound also reflects well off. You know the polarics, right? The polarics. This is the main thing. You had to say that X-rays were ionizing, and if it's ionizing, it has enough energy to damage cells. And remember, if it's an unborn baby, the cells are still what?
Developing.
Developing.
Yeah. Do you want the baby to come out looking like what doing? Okay, I'll understand that
Yes,
if
sir.
if like these cells mutate and those mutated cells reproduce and like it repeats itself, eventually the baby's gonna come out with birth defects. Are you understand what I mean?
Yes,
Yeah.
sir.
Yes.
Yeah, like webbed foots or webbed feet, all kind of madness. You know what I mean? So you know what that's.
I did put that the X-ray was dangerous for the children, for the unborn babies.
Oh yeah, don't put children. If I like, please someone
No,
didn't put children.
no,
Please someone didn't put children because it's our unborn baby, guys. It's our unborn baby.
no, I did put the unborn babies, but I was just saying children.
Lion.
Hey, it's our unborn baby. All right, Ole had to eat this question up, boy. Ole had to eat this question up. Had to.
Yes,
Hey, let me not stick. Tell me, what kind of lens is that? A divergent or a convergent?
conversion.
Conversion.
Convergent. So, like, after it passes through the lens, wait, take a second. It's going to want to converge at the what?
The focal point.
It's going to want to converge at the focal point, yes. So, let me just.
So I did that same thing and
Okay, so is this correct?
nah.
No.
Is this correct?
Ye-
Wait,
um, yeah.
yeah, that's correct.
So This make me feel real happy, you know. Like I mean I could have draw it myself, but the way how they give you most of it already, and like I feel real glad.
Claude, ChatGPT make a dumb diagram. Like make a something.
Let me see it.
Yeah, what? When you complete any diagram, all you understand that, look at the rules, right? You're gonna draw a ray of light parallel to the principal axis, and after it passes through the lens, it's gonna converge to the focal point. That's the first rule. The other rule is if you have a ray of light that passes through the optical center, it's gonna go straight through undeviated. Yeah.
Yes, sir.
See, if you like it, if you draw it perfectly, it's supposed to look like this. I'll have that unlocked.
Yes, sir.
Define the term focal length. Right. Focal length of a convergent lens is just the distance from the optical center of a lens where rays parallel to the principal axis converge after passing through the lens as well. We know this. Did you guys put
Yeah.
it?
Yeah.
Yeah.
So you had to state that it was the distance from the optical center
Mm-hmm.
to the focal point.
Yeah.
And then you had to say it's the point where rays of light parallel to the principal axis will converge to after passing through the lens. And that's one mark.
Yes, sir.
I already answered the question. On the grid, on the diagram in figure 8, complete the parts of the other two rays. We do that.
So I was going to draw over the whole thing.
No, Nikolai, just no. But I'll let you get through this. 4 marks in the
Yeah.
bag.
4 marks in my
Yeah.
pocket.
Alright, we nearly finished with the paper. Figure 9 shows a ray of red light from a source incident on the phase PR of a glass prism at point S. The source emits visible lights. Okay, here what? Immediately, what medium is this?
Yeah.
Where's your refractive index at A?
1.
I showed you what we to find a refractive index at glass.
Yes,
And what
of
do we
course.
find? So predictable. So we gotta find the refractive index of glass.
So there was wait, and they tell you was drawing the refractive ray as well?
Well, let me do that. Did they say that?
I think so, yeah. Because I know how to draw something.
Mm. Oh
Yeah.
yeah, on figure 9, draw the refracted ray at phase PR and the ray emerging from phase PQ of the prism. No problem. So somebody remind me. What would I call this line here?
The boundary line.
Because it separates the air and the glass.
Mm-hmm.
Okay. And you see that it's 90 degrees each other. Cool. We're going from a less dense to a more dense. What are we doing here?
They're going towards the normal.
Well, answer my question. We're going from a less dense to a more dense or vice versa. What are we doing here?
Well, less than some others.
If you're going from less dense to more dense, you're gonna bend what?
Towards the normal.
Exactly. You're gonna bend towards the normal. Let me check if this diagram was correct. Yeah, it will work. And so after it's going to what? Like, okay, if it were to go straight through, it would look like this, right? It'd look like this. But since it's going from a less dense to a more dense, it's actually gonna bend. It's gonna bend
Because
towards,
it's slow down.
yeah. And we know that R would be less than what?
I.
I.
You know that. It's telling us the angle of incidence of the ray is 42 degrees. So this is 42 degrees here. And it's telling us the refractive index of glass for red light is 1.5. No, that's not, they don't want me to find refractive index of glass, Nikolai. They want me to find the angular refraction.
Oh yeah, because I did the sign of this.
Yeah, so here what? Ni sin I is equal to Nr sin R. Where's the incident ray? It's in where? Where is it? The
Yeah.
incident ray. It's in where?
here. In here.
So I'm gonna replace Ni with what?
1.
Do I know what the incident angular incidence is?
There's 42.
do I know what the refractive index of glass was? Because, okay, here what I say now, right? The refracted rate, where's the refracted rate?
In the inside in glass.
It's in glass. So I can put 1.5 for that. Was the only unknown?
The angle of refraction.
So I should divide both sides by?
1.5.
Yeah, I may do this, right? Leon, may I get through this question?
Yeah, yes, I got fullness.
So we got to find what now?
Sine
Sine
inverse.
R, well for R.
To do that, we're going to find sine inverse of this whole thing.
Yeah.
Let's do that quickly. So sine inverse, sine 42. Advanced people, make sure you calculate in degrees, please. Yeah, let me know if I get that.
Yes, sir.
26.49. They set to 3 significant figures. So if it's 3 significant figures, I'll be 26.1.
26.5
5 what?
degrees. Yeah, I may try and put in that.
Right, everybody get that?
Yeah.
Yes, sir. Hey,
Right.
sir. I cooked this exam.
Happy to hear that. Happy to hear that. Right. So let me tackle part 2 now. So on figure 9, draw the refracted ray at phase PR. Right, we do that. We okay with that?
Yes, sir.
Yeah.
Because again, we know that the angle had to be smaller, and we found it to be 26.5. So we're gonna plug in for this. Can't put 26.5. Isn't that what we just found for?
Yes, sir.
And then they want us to draw the ray emerging from phase PQ at the prism. Label this ray T. So let me ask you that question, right? And don't forget to pay an arrow. You have to pay an arrow too. This is a refracted ray. So over here, going from glass to what?
Glass to air.
Yeah. Speed.
So if you're going from glass to air, it's gonna bend away from the normal or bend towards?
Away.
Away.
It's gonna bend away because you're going from more dense to less dense. So here, what I would do, I would draw my normal. I looking like my normal. Tell me what I think is correct. What I think is correct?
Yeah. Nah.
That'd be parallel to when they did full center.
Yeah. That's good intuition. But what I was trying to say is, if you're going, wait, you sure?
Huh?
Sure about that? Check something.
Mm,
Check something. Verify something. No. No, it would not. That's why I know. Yeah, it would not. It would not. You can't do that.
I'll make it like not parallel, but a little bit higher.
Okay, here what I'm saying again, right? Here what I'm saying again. Earlier, we are going from glass to air, which is more dense to less dense. So here what I'm saying, right? If this is the angle here, then the angular refraction has to be what? Less or more?
More.
More. So you want something that looking like this. This angle here had to be more. Yeah, watch. This typically what it does look like.
Yeah.
So let me run it back again, right? If I am going from a more dense to a less dense, what happen? More dense to less dense, what will happen?
Really, really speed up.
it will speed up and it would bend towards the normal or bend away.
Away.
Come on.
Right. How much of you guys figure this out?
I get bad input like
I
so
get
much.
And you have to show it bend away from the normal. And so in this instance, R would be more than I.
Yeah.
If R is not more than I, you wouldn't get the mark. Yeah. Nikolai, you get through this?
Yes, sir. How much marks was for this again?
2 marks.
Yeah.
So 1 mark for this, 1 mark for this. Right. And we're supposed to label this what? T. They wanted us to label this rate T. Sure. Quality. All right. Figure 10 shows 3 nuclei, E, F, and G, of different atoms, 2 of which are isotopes. So I want to just, guys, remind me quickly. If I have an element Z, well, I'll just say, you see we have an element T, right? What does this represent?
Yeah, Tom.
Mass.
Mass number.
The mass number. Is it like, it's typically like what way? Like, I don't really like chemistry, but
No, isochemistry.
and it's like A, Z, well, it's just a general representation.
Yeah, and physics.
But like, the one on top is the mass number.
Yeah. And the
And the
one
one
below is
on the
atomic
bottom,
number.
you can say atomic number, you can say atomic mass. Now, the mass number is the sum of the what two things? Protons and the what?
Which ones and
Neutrons.
which ones?
Neutron.
And atomic number is just what?
Electrons.
Proton.
Protons.
Proton.
But
Well,
you
yeah.
understand protons and electrons should be the same, right?
Yeah.
Okay, good. So define the term isotope. I didn't write the answer here, but
Same
I'll
number
write
of
it fast.
protons.
Isotopes are atoms of the same elements that have the same number of what? Starts with P.
Proton.
Proton.
But what?
Different number of neutron.
Number of neutrons.
So in other words, the atomic number is going to be the same. So atomic number will be same. Or what would be different?
Mass number.
I'll understand this.
Yes, sir.
I'll get that 2 marks or no?
Yeah.
Yes, sir.
Yeah.
Okay, good. Oh, I was doubting myself for no reason. Is the AZ, yeah. Yeah, that was like the standard way to represent it. Put on Nikolai there. You know, Nikolai doubt himself.
Yeah. I
Alright,
think
so
it's not that way. Sir, I did have 2 lines, one for the atomic number, one for the
hey, Claude create this. Don't worry about this. Forget about this. E, F, and G. So here what? For E, how much protons and neutrons are there? So like the empty circle is the proton and the darker circle is the neutron. So how much protons and neutrons you have in?
wasn't it 16? 1, 2, 3, 4, 5, 6, 7. Huh?
Everybody get 16?
Yes, sir.
You know them snail eggs that has been drained? That's what it's looking like.
Yeah.
So it will be 16 here. And what's at the bottom?
8.
Alicia? Proton. I just verify it. 1, 2, 3, 4, 5, 6, 7, 8. Yeah.
Yes, sir. I know that was oxygen one time.
Yeah. That's oxygen. And let me look at F now. So F. How much protons and neutrons it have? 1, 2, 3,
I think it
4,
was 17 they did put.
5, 10, 11, 12. It's 17.
Yes.
And how much neutrons do we have?
9.
8.
Neutrons? I thought it was protons.
What's the boy? Oh, yeah, boy. 1, 2, 3, 4, 5, 6, 7. Yeah, 9.
Yes, sir. Hey.
Let me just make sure I'm not confusing anybody. Hey, on top is protons plus neutrons, eh? And at the bottom is protons. I don't know why I was counting electrons just.
I get that. I get that. I get that. I get that.
Big up, big up, big up one time. And G, how much protons and neutrons we have? 1, 2, 3, 4, 5, 6, 7, 8. 15. Okay, that's 15.
Yes, sir.
And the bottom half is 8.
Wait, I'll get 15, right? Like, let me make sure Claude didn't make a mistake. I'm gonna count it myself. Waiting from the original thing he sent. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, I'll get 15, right?
Yes,
15?
sir.
Yeah, 15 on top.
Yeah, Liam, you had got 15 on top.
Yes, sir.
And let's find out my protons now. So like 1, 2, 3, 4, 5, 6, 7, 8. All I had got 15 each.
Yes, sir. I get that correct. I get that correct. Oh, thank God. Thank God. Thank God. Thank God.
Yep. Big up, big up. So let's tell me fast. Which ones are isotopes?
And
E and
G.
G.
E and G,
Yeah.
E and G, because they have the same atomic
Proton.
number,
Yeah.
Atomic
which is the same number of protons. E and G. I'll get that one. I'll get that marks, right?
Yes,
Yeah.
sir.
All right. A certain radioisotope is administered just prior to a severe medical procedure. This graph in figure 11 shows the activity of the sample of the radioactive isotope given to the patient over a few hours. So, like, could someone just remind me what half-life is? Half-life is just what?
Just half the original
The
value.
time taken through the
Quantity.
period or something like that. And it's the time taken for something.
Right. It's just the time it takes for a quantity to be halved. A more concise definition would be the half-life of a radioactive nuclide is the time taken for half the nuclei in a given sample or the activity/mass to decay. Right? It is a constant for a given isotope.
If you
So
input that exact thing, but you put some of the keywords, you'll still get a mark.
yeah, you're getting mark, you're getting mark, you're getting mark.
Okay.
Yeah, you're getting mark. So all half-life, okay, if you have a radioactive nuclide, you need to understand it will decay. And we're just trying to measure the time it would take for it to decay to half its original quantity. That's all. So using the graph in figure 11 and assuming that all radioactive substance stays in the patient's body, state the original mass of the sample. Or what's the original mass?
80.
80 milligrams.
80. 80. I'll put that right.
Yeah. Yes, sir.
Okay,
So you
good.
know we locked in.
Yeah, we looked. Determine the average half-life. So we gotta find at least more than 2 half-lives. So it's half of 80.
40.
A
So
surprise
this look
cloud
like the
generate.
exact. So this look like the exact example you gave us in the crash course, sir.
Okay. But like a surprise cloud generate this diagram correctly. Are they a surprise?
Yeah, it is.
Like in one shot too.
Yes,
So
sir.
the first time and a half is just what?
It's 10
10
hours.
what? 10 hours,
10
right?
hours.
To find the second time and a half, I'm gonna look at 20.
Yes, sir.
And that time and a half is gonna be given by this. And that can like what?
10 as well.
And if you wanted, it could go again. That can like
That look like 10 as well.
Yep.
So you put 10?
So that again?
You did put 10, it's 10, right?
It's 10, it's 10, yeah. Yeah, it's 10.
Okay, well I put 10.
Yeah, that's correct. You find the average, right?
Yeah.
So the average time and a half would just be equal to the first time and a half plus the second time and a half plus the third time and a half divided by what? 3, right?
Three.
I use 3.
Three.
If you had to use 2, you'd have to divide by 2. So it's just 10 plus 10 plus 10, which divided by 3 is
10.
10 what?
Huh?
10 what? 10 what? 10 what?
Hours.
Hours, yeah. If you put seconds, they give it wrong, eh?
Yes,
Nicola,
sir.
you put seconds.
No,
I feel you put seconds enough.
no, I didn't put anything for that.
Oh, yes, so put, you can lose a mark then. You have to say the units. In physics, you have to say the units. Estimate the mass of the radioactive substance that remains after 4 half-life. All right, after 4 half-lives, right? That you're gonna multiply by half how much times? After 4 half-lives pass.
Times. 4 times.
So it's gonna be reduced to what? 2 to the power 4 is 60.
Yes,
So the
sir.
sample is the mass is gonna drop to what?
1/16.
1/16 is original amount. So what was the original amount?
80 grams.
Right. So you could say 80 multiplied by 1/16. I think you should get 5.
Yeah.
Yes, sir.
That's it. That's it for the paper.
Yeah.
Yeah, well, those are really easy paper.
Mm-hmm.
Nothing hard, like no generators, no Fleming's right hand rule. A little lucky boy, a little real lucky. Real lucky boy. If that had come, I'd be singing on a different grace.
Yes, sir.
This is probably the hardest question in the paper, which not even that hard.
No.
Because they could have bring a question with cladding and the core, a fiber optic, but they didn't do that. Very straightforward paper. So like on average, how what mark would you get?
95.
Liam, you get 95. Big up, big up. Nikolai, what you get?
I lost 1 or 2 marks here and there, like the units and like the thermometers. So I'll probably get around 90 or somewhere around there. Probably in
Well,
the 80s. I wouldn't say 90s, 80s.
that's good. That's good. Anybody else want to share how they feel I do?
So I think I got 95.
Hey boy, that's his badness. So that was it for the solutions video. Yeah, take care everybody.
So when we start any paper ones?
We will start people once tomorrow. I'm too tired.
Yeah,
That's
please.
Yeah.
Yes,
I
please.
hope you do.
I'm
Yes,
so
please.
tired.
Start
Right now, I
tomorrow.
like tweaking. I'm tweaking right now.
I am tweaking too.
So what time tomorrow? The same 4?
Wait, take a second. I can.
Mm.
Yeah, big up
Hi
everybody
guys.
who pass
How
as
only
well.
fun it was.
You see?
How only fun it was.
I find it was nice. I mean,
It
like
was
that
okay for me.
area under the graph. I did not know like you're supposed to put maths into it now because I know you in physics you had to have formulas.
Yeah, I know that too. And I was going when I was in the exam, I was going on base what I know and what I remember. So hopefully it's
Wait,
enough.
guys. I had to go now. I had to go now. Like, I had to go see about my car.
Listen, bye.
So
Renisha, we go talk. You just call me on
okay,
WhatsApp. I'll call you on
okay,
WhatsApp. You call me on WhatsApp, right? Yeah,
okay.
guys. That was easy. I hope I get through, right?
Yes, sir.
We'll see you guys with the paper ones.